All right, so we have some data here. A car is braking, coming to a stop. Um, and what we'd first like to do is plot this data on a set of axes. Given we only have a few points of data, but we can make a graph here. So let's go ahead and do that. We are graphing this over, I'll just graph 1, 2, 3, 4, 5, 6 points. 1, 2, 3, 4, 5, 6. This is time measured in seconds. And what is my velocity measured in? Velocity is measured in feet per second. All right, at 0 seconds, how fast is this car going? It's going 100 feet per second. So here's a point. Let's make a scale before we go too much further. 50, 75, 25. All right, so at 0.3, so 0, 0.3, 0.6, 0.9, 1.2, 1.5, 1.8. At time 0, we have 100 feet per second as our velocity. At time 0.3, we have 88. At time 0.6, we have 74. Time 0.9, we have 59. 1.2, 40. 1.5, 19. And then 1.80. Okay. Is that all we were asked for? Plot the given data on a set of axes. Okay, good. Then what? Estimate the total distance traveled during the time breaks. Okay, estimate the total distance traveled during the time the car was using the brakes using a middle Riemann sum. Okay, so let's go ahead and do that. In fact, I am going to, let's do some edits on the fly here. Actually, let's just go back, and we know we need to use a middle Riemann sum. Oh, with 3 subintervals. Okay, this makes sense. So with 3 subintervals, that means that I am going to use basically every 0.6 seconds. So my rectangles are going to be like this. So basically, for part B, x naught is equal to 0 seconds. X1 is equal to 0.6 seconds. X2 is equal to 1.2 seconds. X3 is equal to 1.8 seconds. Which means my midpoints are what? X1 bar is equal to 0.3 seconds. X2 bar is equal to 0.9 seconds, and X3 bar is equal to 1.5 seconds. So now let's find a Riemann sum. Basically, we're doing midpoint Riemann sum at 3 seconds, or sorry, over 3 intervals. So what is the delta x? The delta x is going to be what? 1.8 seconds is the full interval, and we're dividing that into how many pieces? 3. So that'll be 0.6 seconds. So 0.6 seconds is the width of the interval, and now I want these 3 values. V of 0.3, V of 0.9, and V of 1.5. So equals 0.6 seconds times, what's the velocity at 0.3? 88 feet per second. At velocity at 0.9 is 59 feet per second, and 1.5, 19 feet per second. So if we get a final estimate there, I get an estimate of 99.6 feet. So that is the estimate from the midpoint Riemann sum. All right, part C. Calculate the total distance traveled by computing L6, R6, and what does this mean? So let's compute L6 and R6 first. I'm still looking at 3 interval. Oh, L6 and R6. Now I'm using 6 intervals. So let's go back here and see if we can. I'll develop one of these in great detail, and I might leave the other one for you. But basically, we want to do this over 6 intervals. So how are we going to do that using the left sum? So if we're going to do a left sum with 6 intervals, we probably need a new delta x. So that'll be 1.8 seconds over 6 subdivisions. So that'll be 0.3 seconds. So L6 is going to be equal to 0.3 seconds. And then where am I sampling? I'm going to be sampling at the left point of every rectangle. So that'll be v of 0 plus v of 0.3 plus v of 0.6 plus v of 0.9 plus v of 1.2 plus v of 1.5. So do I have all those values? So that'll be equal to 0.3 seconds times basically the first 5 values in the table. 100 feet per second plus 88 feet per second plus 74 feet per second plus 59 feet per second plus 40 feet per second plus 19 feet per second. So let's get an estimate there. 100 plus 88 plus 74 plus 59 plus 40 plus 19 times 0.3. Okay, I am getting an estimate of 114 feet. But then, what about R6? So what's going to change from L6 to R6? What about delta x? I have the same number of intervals, so the delta x should still be 0.3. But what about the values where I'm sampling? Now I'm going to be sampling at the right end of every input, the right end of every interval. So I'm not going to be looking at 0, 0.3, and so on. I'm going to be looking at 0.3, 0.6, 0.9, 1.2, 1.5, and 1.8. So essentially, it's instead of sampling the first 5 velocity values in this table, I'm going to be sampling the last 5. So there's some overlap, but you might expect correctly that the distance here is going to be lower. So let's go ahead and do that. So 88 plus 74 plus 59 plus 40 plus 19 plus 0 multiplied by 0.3, I get 84 feet. So those are 2 of the sums I was asked to compute in part C. The other one is 1/2 of L6 plus R6. What does this notation mean, first of all? So basically, I want to add these 2 things together and cut it in half. You might recognize that as an average. I want to add 114 plus 84, divide that by 2, and I get 99 feet. So this may seem familiar. It may seem like the midpoint formula. But if it was the midpoint formula, then we would get the same number for the midpoint Riemann sum and what we just did, but they're off by a little bit. So one thing I want to point out is that in the midpoint Riemann sum, what are we taking the midpoints of? We're taking the midpoints of x values. But in the thing we just did, we took the average, or which is a kind of midpoint of the values of the Riemann sum. So what is it that you're averaging? Is it the x values or the y values? That's basically the difference between what I did in part B and what I did in the very tail end of part C here. Not part D. Part D is still to come. Part D, assuming that V of t is always decreasing, what is the maximum possible distance the car traveled before it stopped? Okay, so Vt is always decreasing. If Vt is always decreasing, then what's most likely to happen is we have like a smooth curve that kind of unites all these things. But we don't know that for sure. Let me see if I can get a better idea what this is looking for. The Vt is always decreasing. What is the maximum possible distance the car traveled before it stopped, and why? I think the maximum possible distance the car traveled before it stopped, that maximum is probably going to come from our left-hand endpoints, because even though it probably doesn't look like this, like we only have a few points of data. But this right here is a function that is decreasing, because as I travel along this function from left to right, at no point is the y value increasing. That's maybe when we say a function is decreasing, that might be a more telling way to say that it's increasing. Basically, your function, sorry, to say your function is decreasing, what we're really saying is that as we go from left to right, so as x values increase, the function fails to increase. It just never increases. But we can have these big chunks of time, like from 0 to 0.3, where the velocity doesn't change. So it probably doesn't look like that, because this is not even a differentiable function. I have all these hard corners. But what if we do this instead? What if maybe it's horizontal for a large chunk of time here, but then it decelerates very abruptly, so it's not actually a hard corner. So it can be differentiated. What if it does that at every interval? Well, it still looks like it's mimicking pretty well a left Riemann sum. So I think our left Riemann sum is kind of like our theoretical maximum here. It's probably not that high, but I think I can certainly say it's no higher. If this function really never increases, if it's decreasing the entire time, 114 is the absolute maximum distance this part could cover in that time.